questions, but okay, but that's if you know what to do. All right, so as usual, let me review what we did last time. I hope this is useful. I know I blow a lot of time on reviews. I remember one time I think I gave, not this class, but one time I started reviewing and sure enough a half hour passed. And I started redoing the entire lecture from last time because I'm weird. All right, so let's see, what do I want to say here? Well, all right, so let's talk about, remember we're doing mixing liquids. We always know that gases mix, because, I mean, yeah, of course they mix. That's absurd. Of course they mix, but liquids don't have to mix. And I'm just trying to remember what circumstance. Remember that the thing I told you I don't like about all this stuff we're covering this week and next week is it's just layers upon layers of approximations. And I haven't started approximating anything yet. So I will try to make it very clear when I make an approximation. Remember that the idea is that you look at the vapors of a liquid. Vapors will be in equilibrium with the liquid. We haven't really ever talked about things really not in equilibrium because why wouldn't we? And so the idea was to hijack the information from the vapors and apply it to the liquids. Now this would be delta G of the vapors, and they mix, and of course they do mix. And what we would then do is divide by number of moles, and then this gives us mole fractions. I know I try not to do this to overwrite. I'm basically overwriting my own derivation. I try not to, but I couldn't resist this time. Once I've divided by moles, I've got chemical potential, and now the damnedest thing is this number. We started out with the vapor. This number for the vapor is the same as the liquids once I divide it out by the fact that there's not much vapor. Of course there's not, you know that. So I divided that bit out, and now I've got an intensive variable. Chemical potentials are intensive. And of course at equilibrium, intensive variables are all the same. Remember that was something I brought up a while ago when we did ice floating in water. Not only were chemical potentials equal, therefore any change in chemical potential would be equal. All intensive variables are equal. That's something that defines equilibrium. Okay, the trick is that if this is true for the vapor, it's also true of the liquid. I successfully hijacked the information from the vapor and applied it to the liquid. Now, this is no approximations. All of this is perfect. Now I'm going to blow it. Okay, now that's where, okay, I'll write that out in case you forget. That certainly sounds like a true and false question to me. I have not looked at the test yet, sorry, but it is kind of interesting to me because we are going to really do a lot of very bad approximations from here on out. That it actually really begins right here, by the way, and that's Raoult's law. Raoult's law, which says that the partial pressure, I'll just say A. Well, here, that works, right? The partial pressure of a vapor would be the mole fraction in the liquid times the pure partial pressure. Okay, that's Raoult's law. Now let me change this for the liquid. And here I'll just liquid. It's really the liquid or gas. I'm about to wrote gas, but just drop that. We're doing liquids, right? And this ends up being, let me know the formula, I just want to make sure it's putting this up. RT, Ka, Ln, Ka. You can kind of remember this, and of course it's on the cheat sheet, but Ka, Ln, Ka, Kb, Ln, Kb. It kind of just flows off your tongue, so again, it's kind of easy to remember. Okay, and remember that this is still the delta G per mole. And, okay, and let me also put this in terms of, I'm going to do this per mole. You've got the mixing H per mole. We're going to focus on this guy entirely today, minus T delta mix S per mole. And that means that, I think this is as far as I got last time. Anyway, so, sorry, I'm kind of doing 5 things at once. I'm still just kind of rattled about the camera screwing up on me. So the crazy thing is that this is very, very bad. I mean, if someone just came to me in the street and said, well, would the vapor pressure be diluted from the liquid if the liquid is diluted? I would say yes, and probably the same amount. So my idea of taking ethanol and water and water, and of course the vapor pressure of water is the pure vapor pressure. Obviously that's true. And I diluted half with ethanol. Think of moles, right? Don't think of volume or weight. Think of moles. That would really be a lot of ethanol, by the way, but whatever, it's a detail. I would say that the vapor pressure of water, the partial pressure of water, because it's not nearly an atmosphere, right? I would say go down by half. And that totally makes sense to me, and it's dead wrong, except in just a few very limited circumstances where I said like benzene, toluene, hexane, heptane. I mean, why are you even mixing those, right? So, and we're going to go over why this is very bad. Now, when it does work, so I'll write that works. Oh, I don't like that. Oh, works for ideal. Okay, ideal solutions. And remember that was the mixing volume is 0, and I'll work in proper units. And the mixing change in U is 0, going in the proper units. So this implies that molecules have the same size and they interact with each other the same way. So it'd be like methanol, ethanol, right? They both hydrogen bond to one partner, unlike water, which hydrogen bonds to 2, because it has 2 hydrogens, by the way. It's that simple. And so that's why water ethanol is not ideal, because they have drastically, hydrogen bonds are really significant for liquids. And so the fact that you're missing one in ethanol makes it very different than water. So that's why this would not be true for water ethanol, but it would be true for methanol ethanol or butanol ethanol. Okay, now from this you should be able to show that delta H mix. And sorry, I need to be putting per mole. Again, it's a remember I told you I'm not going to really hold your hands to the fire on that, because you see me forget it a lot. It's just that I want to do everything per mole because I'm hijacking the vapor pressure thermo, and it only works if it's per mole, if it's a chemical potential. So I'm kind of sorry about that. I'm kind of screwing that up. In that case, then the delta G mix per mole is entirely minus T delta S. And again, just even if you just totally forget this per mole thing, that's fine. And based on what we've done, therefore, the mixing entropy per mole is R minus R chi A ln chi A. Remember, it just kind of rolls off your tongue. Chi B ln chi B. And of course, big parenthesis. Let's see. Negative, positive, positive, negative. Delta S mixes. Positive or negative? Positive, right? Positive. Remember, negative, but this natural log's a negative. This will also be negative, so the whole thing is positive, right? Remember, that's good. So ideal solutions always mix. It is entropically driven, right? Sounds like a true and false question. It's entropically driven. They always mix, and it has to do with the fact that the enthalpy is 0, and that comes from here. And in terms of test taking, remember I told you I'm going to focus more on test taking strategies. If you remember that, there's nothing I could ask you that you couldn't answer. I don't like trying to have you remember that, even that kind of quantity, just for a question and stuff. At the same time, I have to admit, there's no way that would work. I'm just saying, all right? And I'll make sure this video gets posted. One last bit, I want to show an entirely different proof of this. And so note what I'm doing is I'm doing another proof of the same thing. And we'll pray that I got a new pen. This is going to be pretty short. So based on these principles here, I'm going to do a completely different proof. I'm going to come up with the same delta S. And just for the heck of it, just because it's kind of neat that you can. And what I want to do is talk about delta S per mole is NRLN VF over VI, oops, per mole N, so that goes to 1. Just wanted it to look, why did I do that? I wanted it to look familiar. Remember, NR ln VF over VI. And of course, I would have to have a partner. So this would be for A, and I have to have one for B. So N and A and B are ln V, and I'm going to drop these F's and I's in a second. Okay, because there's two things. And entropy is extensive, right? Okay, of course. No, sorry, that's not one. What am I doing? Sorry, I mean, that's where you get mole fractions. That's the definition of mole fraction, my bad. Okay, so now what I want to do is, let's see, how do I want to put this? This would be, notice that what I'm doing here is the final volume, here I have to do some stipulations here. Let me do it like this. So the final volume would be VA plus VB. And therefore, F over, actually here, you know what I need to do? I need to write, sorry, I didn't think this through very well, did I? IAR, what I want to do is actually flip these. So notice what I did was I introduced a minus sign and flipped these volumes. And why? Because it's going to start to look really familiar here in a second. Yeah, plus, sorry. Man, I'm a little out of it. The video camera's still bothering me. Okay, so therefore, what I want to do is point out that VI, A or B, I'll just stick with A, would be equal to its mole fraction, right? Now, what's going on is that if A and B had the same volume per mole, then the contribution of A divided by the total would have to be its mole fraction, right? That's kind of logical, right? So if they had the exact same volume per mole and say that there's 1 mil in every mole, then and I put the two together, I end up with 2 mils, right? So this is equal to the mole fraction. Okay, so then delta S per mole minus R chi A ln chi A plus chi B, exact same equation. Okay, so anyway, there's really not much point to this. I shouldn't have blabbered so long about it. I do like pointing out that there are multiple ways of doing things, and that just kind of means that everything makes sense. See, I've got here, by looking at vapors mixing, and we've already done gases mixing. Here, I am kind of hijacking. I don't even really know what my justification is here. Maybe that this is the entropy of vapors mixing, and per mole that's the same as the liquid. I don't actually know if that's valid. I think you can just kind of phenomenologically say that when you mix methanol and ethanol, it's got mole to mole, and they're the same size. It has twice the pool to swim in, and that would, you get ln2 to your entropy. So regardless, maybe it's just luck, but it does come out to be the same. Let me graph this so you have some idea of the magnitude. I know this may not stick super well in terms of how big these numbers are. It's something that I kind of struggle with. I know that, here's my just rule of my order of magnitude calculator. I remember that a CH bond is about 100, oh God, I think it's 100 joules per mole is the energy. So anything on that, 100 kilojoules per mole. Anything on that scale is by definition gigantic. If I see a reaction that has a minus delta G on that kind of 100 kilojoules, 100 kilojoules, that's really big. That's an explosion, right? So with that said, let me show you what T delta S looks like. And let's get used to seeing mole fractions. I always put these in mole fractions of the solvent. I'm going to call B the solvent a lot from now on because we're going to be doing a lot more with this. B will always be the solvent and A the solute. Now that's kind of stupid because over here A is the solvent, over here B is the solvent. I'm just going to stick with something to be consistent, and you'll see in a minute. So again, magnitudes, this is T delta S, and I believe I did that. I did this at 25 degrees Celsius. That's important to know. T delta mix, and the magnitude is 1.7 kilojoules per mole. Okay, again, 100 kilojoules per mole is about as negative, right? So remember, delta G is minus this. And here, let me put that in. So again, this is an ideal solution. This would be delta mix. And of course, this would be minus 1.7, the same. This is relatively relatively small. I wouldn't ignore it, but compared to any reaction that I would care about, I say that when I see delta G's for different processes, for reactions, I always see around minus 30 is a common number. Again, a gigantic one would be 100. 1.7 is definitely, or I guess delta G minus 1.7 is definitely smaller potatoes, but notice this isn't really a chemical reaction, right? It's just mixing. It's kind of a chemical reaction. So it kind of makes sense. It kind of doesn't have a very big number. Notice though at the same time, if this is all you've got, then it will happen. So if a process is negative, even if it's very, very small, it will still happen. It doesn't seem like much would stop this from happening because again, that's a small number. That's true. Let's get into delta H's, which you stopped at. Okay, before we get into delta H's though, let me do some more graphs because for one, we're going to be doing even more graphs. I just want to introduce you to some of these. Number two, it gives me a chance to put graphs on the tests, which was missing in test 2, and I really regret that. I think that would have been one thing I could have done different. What I want to do is graph Raoult's law, because we're going to see lots of these here in a minute. In a minute actually, and then next week and the week after. Okay, so the point of this is let's look at the partial pressure of A and the partial pressure of B, and then we're going to look at the total. So if I draw this would be PB star, and I'll make the A star here. Okay, I can't draw stars very well, but so anyway, this guy would be for PB. Obviously, you can tell because it starts at 0 when there's no B present, and the same for A. I'm trying to draw a straight line. There you go. Okay, and then of course the total would just be a linear sum, and that's always going to be true. Now, of course, do remember, or maybe don't, remember that these pressures would be on the order of like a few hundred pascals. Remember that atmospheric pressure is 101,325 pascals, 100,000 pascals. This is about 100 pascals. That's a good number. Don't worry about that really at all. Don't think that this is atmospheric pressure. It's like I said, about 100 times below that. Or more, 100, 1,000 times below that. I just want to look at relative, relative to water and ethanol. They're both small numbers, but this would be the total partial pressures of water and ethanol, and they would be around 600 pascals. Sure, whatever. And the rest is made up by air, oxygen and nitrogen, 75% nitrogen, about 25%, a little under, 20% oxygen. I forgot off the top of my head, but anyway. We'll just ignore those gases, so you don't ever have to think or worry about the other gases when you look at these graphs. Now this, all right, so now notice that this is Raoult's law. The way I know it's Raoult's law is that these lines are straight. And that's implied, here I'll just write Raoult's law again. That's the pressure of A, and the same is true of B. Okay, why don't I just do that? I hope that doesn't get you a little bit perturbed, but okay, the partial pressure of A or B is its mole fraction times its pure partial pressure. Now this is the definition of a line with no intercept, and I'm seeing two lines with no intercepts. This obviously has to be Raoult's law, and no matter what, the total is the sum of the two. Okay, now here's, I'm drawing lines, you know, this is for fifth graders, right? What I'm doing is I want to remind you that there's a molecular reason for this. And so I'm going to start doing is drawing pictures of molecules in a box. I've done it a couple of times. And what I'm going to do is I'm going to draw A and B in this box. And I don't know which one's A. Maybe it's the square. I don't know which one's B. It doesn't really matter. What I'm trying to do is draw them roughly equivalently. So I'm not really trying, I might be, but I'm not trying to bias the picture towards A or B being on top or on bottom. And okay, so you'll see what I mean in a second. Looks like I need to use one more A if A is my square. Okay, so again, my point here being that what I'm seeing here, in case it's not clear, is an even distribution of A or B, whichever one you want to call A or B. Okay, so here's the idea. Where do vapors come from in the liquid? Right, the bottom or the top? Right, so I'll actually explain, third water. Third circle. Looks like I got 1, 2, 3, 1, 2, 3. All right. So what happens is, where do vapors come from? Of course, they come from the top. So, and if one comes to the top, remember that this is equilibrium, so I need to draw little arrows going up and down. The idea is that if these are mixed well and rather homogeneous, and actually, I mean extremely, perfectly homogeneous, then the vapors come from molecules evaporating on the surface, and the number on the surface would be exactly proportional to their mole fraction, right? It just makes sense. So notice that this kind of childish graph with the 6th grade formula actually tells us about the molecules, not only in the bulk, but how they behave on the surface. Okay, again, overly simple. All right, end of ideal liquids. Let's go into non-ideal liquids, and that's when delta H is going to mess this up, screw up these graphs, and blow this picture. All right, so that's what we're going to drop all this ideal solutions. Do remember that there's that the molecules are the same volume, they interact the same way. But now let's vary the interaction. Let's blow these pressures and then derive a little formula for the new G's and the new, well, we're going to come up with a little formula for enthalpy. And that's going to change the G, and that's what's going to allow things like water and hexane to not mix, nor should they. You see, water and hexane do not mix. Okay, so what do I want to do first? I don't know whether, here, I'll do the graph first. Let's do pressure. And I'll do B. And don't worry about A. A will do the opposite of B. It's not hard. Okay. So now, Raoult's law says that there should be a straight line. Now, I can imagine that there's two potential ways to deviate from a straight line. One would be under. So I'll do the under case. Now, you notice that there's a little inflections to this. I'm actually trying to draw that very accurately since I don't PowerPoint. I do practice my drawing. This has been done very accurately, where notice is that I did actually intend this line to connect back to the Raoult's law dotted line. I did intend that to be the case at high, when B is truly the solvent. Remember, I'm going to call B the solvent. When B is actually the solvent, it's not the solvent here. When it is the solvent, it ought to reconnect back to the pure partial pressure. That would be bizarre if it didn't. But here, again, one of two ways I can imagine a deviation. It's under. I'll do the over case in a second. I'm just saying that there's two ways to go, under or over. And the second thing is it's going to be more screwed up when it's a solute and not when it's a solvent, because when it's a solvent, the pressure of the liquid vapor should be the pure partial pressure, because that's the only thing in the box. All right, now what I'd ask of you is looking at this graph. Now think of low levels of B when B is now actually the solute. How do I want to do this? At low levels of B, what would I, so I have to make a decision. O is B, and let's say that the squares are A, and we're going to be working in this region, so I'll draw like this. Okay, so you know what I'm talking about. What do you think is happening? What do I have on the surface? More A or more B? More what? What did you say it? A. Why? Because that's right. What? Just because I'm doing this, I don't mean to be sarcastic. I'm sorry if it's not. Right, so I have more A. I have more A on the surface than I should. And why? That's because they have some weird interaction. They have some weird interaction, and A doesn't allow B to float. So it's a kind of a bully in that regard. And yeah, so A is stopping from B from getting to the surface. It's basically, there's some there. I mean, it's not too absurd. But for the most part, B, and you know, there's still some A inside of it. A is knocking B out of the way, at least when it comes to the surface. So you notice that I am not trying to draw this evenly. You know, there's a little bit, looks like there's one, maybe two on the surface, but there's a heck of a lot of A. So therefore A is at the surface. Okay, so again, silly little graphs actually tell me about what happens to molecules. Here, let me just draw one more, because I don't feel this like perfect yet. Okay, anyway, so yeah, they're pressing it down. And likewise, there's another way of doing this. PB star. Camera just do something? Is the camera okay? Yeah. Okay. Yeah, I'm just kind of freaking out about it. I did take it on myself. Anyway, all right, so there's another deviation possible. Notice I still do that kind of inflection towards the high chi B limit. I still do that inflection because, again, the partial pressure should behave itself as a pure solvent when it's a pure solvent. And as before, you could imagine that if I could take a microscopic picture of the box, B has bad interactions with A. A is basically trying to push it out. And we're going to explain how to know this in a minute in terms of, obviously what I've been getting to for a long time is that this is because the delta H's are not right. Well, they're not zero. By not right, I mean zero. There you go. You see, there's too much B at the surface, and that's why vapor pressure is too high. It's not A is not allowing it to get inside of the box, so it has to go to the surface, and there you go. So it's pretty elementary. All right, so molecular pictures, simple graphs. Now, as I'm talking about the deviations, remember I said Raoult's law is horrible. We were doing Raoult's law up there. These are ideal liquids. These are not ideal liquids. And as I mentioned, Raoult's law is extremely bad. All right, now this bothers me quite a bit. I already mentioned I really don't like this material. Here's how they did this back in the 1800s to deal with the fact that they figured this out. I don't know how they did it, cowhead balloons or whatnot. So they came up, well, Henry, whoever Henry was, I meant to look him up before class. I'm sure he was somewhat interesting. Actually, I'm sure he wasn't. But anyway, so this is what they did. And I'll do the low pressure. Well, I'll do both. Why not? Okay, again, these are non-ideal because Raoult's law is not being followed. And I'll do the case of B. Let me do the low pressure one. The low pressure one. And that's where it goes downward more than it should. And not quite exactly the same as I did before, but that was my intention. Okay, now what happens here, when B is the solvent, you're going to have Raoult's law followed. Everything's fine. Sorry, I can't draw. And this is the part that I want to throw up blood. I might throw up on my cat. This is what you do. You actually say that when B is more of a solute. Solvent solute. When B is the solute. Wait a minute, what have I done? No. Sorry. My bad. This, okay. Okay, again. This is whacked out beyond words. What you say is that you have linear behavior at the dilute regime. It's just that if you carry it forward, you hit a different partial pressure, different pure partial pressure. So let me write that down. Different pure partial pressure. So you redefine the pure partial pressure, and I'll go over more of this in a minute because this is Henry's law. Henry's law says you do this and K is the coefficient. Okay, again, Raoult's law says everything's aligned, but almost nothing follows Raoult's law. You tend to see this type of behavior half the time. So you divvy it up in two parts where B is the solvent and it obeys Raoult's law. At the solvent size, it'll do Henry's law, where you just redefine the pure partial pressure and assume that it has somewhat linear behavior. What you do about this, I'll get to in a minute. All right? This is ridiculous in my opinion. No one should do this. No one should even study this in my opinion. Henry's law does have usefulness for talking about gases and liquids, and I'm going to do that in the next hour. But this is just people taking equations that don't work and multiplying by something until they do. And that something is defined as the thing that makes it work. And I don't care for this at all. I think this is an awful thing that anyone even thought to do this, because it automatically works, right? Except unless you're here, in which case nothing works. So, with that said, and before I get angry and start tearing the board down, part of this place to the ground, what Henry's law, and I'm going to do this, I'm going to do an example. Sorry, I'm just thinking about what I'm doing on the test right now, so I've been going a little bit. Henry's law is good for calculating gases in liquids, because you know that gases dissolve in liquids, and that's really important for diving, and we do lots of diving because we build structures with bases underwater, like bridges, and now more and more buildings are being built where the base is actually underwater. So you need to be aware of that. Free divers can only go so far because nitrogen in their blood and all that. Henry's law is good for that, and I'll go over some examples in the next hour. But for the most part, this is just pure BS. This is just an empirical factor that makes the equations work because the equations are wrong. That's really what it is. Okay, now while I'm not bashing Henry, I'm glad he's dead. Now you can imagine, I won't draw this, if you go over, then the Henry's law is just above the partial pressure. I won't draw that because it's kind of childish. Okay, and I've got some examples. I'll do those in the next hour. And let's see, I'm going to make a little graph. I'm going to make a little graph here of what's what in terms of ideal. And by the way, for this, I'm just hilarious. Stupid on stupid. Ideal solutions, I got rid of it. Ideal solutions follow Raoult's law. This is called Ideal-Dilute. Okay, this is called an ideal-dilute solution. The idea is that you've got a solvent-solute system that's kind of close to one end or the other. So B, if this is an ideal dilute solution, if we're over here, B is the solvent, and it's obeying Raoult's law. If B, and notice I didn't draw A, but it's just a mirror image of B. If I had A, if there's not much B, then A is the solvent, it's obeying Raoult's law, and the solute, which would be B in this case, is obeying Henry's law. Again, the idea of an ideal dilute solution is that you have a dilute solution, and the solute is obeying Henry's law. The solvent always obeys Raoult's law. So I just said a handful. Tell you what, let me write it down in a little chart, so you can kind of get it all down. I don't want you memorizing this, but I'm not quite sure what else to tell you. So let's do the ideal. An ideal solution where everything follows Raoult's law. Now in this case, the chemical potential of A would be the chemical potential of the pure. So I'm using stars when I'm talking about pure substances. And this would probably be the number in the table in the back of the book. And there we go. Am I missing a chi A there? I think I should have a chi A RT. I have to look that up. I'll let it go for now. Anyway, this is how the chemical potential of A changes, and here's how the chemical potential of B changes. And they're the same, except that I've got a B instead of an A. Okay, and so that's really boring. And then we've got ideal dilute. And remember that I said I would make B the solvent. And this is exactly the same. Sorry for my shorthand. And this guy is different. Okay, this is where it gets a little bit more interesting. Okay, the new chemical potential is the old pure chemical potential plus RT natural log. So remember, if you get anything out of this, remember that chi A is Raoult's law, and that is the partial pressure over the pure partial pressure. And so what you're doing with Henry's law is you're redefining the pure partial pressure to just some number that works. Right. So I'm going to mentally walk myself through this, and maybe that will help you. Okay, ideal dilute. If it was just ideal, the pure partial pressure would be the pure partial pressure. And the partial pressure would just scale with mole fraction. And that's why I would have mole fraction times pure partial pressure divided by pure partial pressure. Remember, that's the initial pressure. And that's why I would get this equation. In the ideal dilute, the pure partial pressure has been redefined. It doesn't cancel out. It can be anything. It just depends on what I measured. And there you go. You're done. The solvent will always behave itself. It's always Raoult's law, because how could it not behave like a pure solvent when it's a pure solvent? Of course it does. So that was kind of easy. Okay, next bit is, now, there's only one reason I bothered to go over all this, is that there's kind of a savings grace. I know I've been trashing all this Henry's law, ideal dilute solutions, yada, yada, yada. I know probably more than anything, this seems like just a bunch of stuff to try to remember. And you know, I always tried to keep this down when we were doing gas expansion. You kind of miss that now, don't you? I do. Because I know that really well, and I try my best to tell you, you know, how to memorize as little as possible and just let your intuition flow. That's still true. This, it's not as easy. Okay. This does have a saving grace in that I can describe this behavior using a phenomenological model. Remember I said that a long time ago. Okay, so deviations from ideal and ideal-dilute, I'll get into that in a second. That part in between when you're like 50-50, you know, and you see you're all kinds of curvy, like right in the middle. Okay, deviations from ideal, from either Henry's law or Raoult's law, brings up the concept of activity, which you learned a long time ago when freshman, and hopefully, and you must have learned this in analytical, I don't know, but you must have learned this in analytical. Activity is the effective concentration of something. This is where it actually comes from, right? And what happens is, effective concentration, whatever the heck it is that you were analyzing in freshman and analytical, and it got brought up like, well, okay, so this equation doesn't quite work, but that's because you have to work with the activity, the effective concentration. And that sounded BS-y. It is. Because, right, that's exactly what it is. What activity is an empirical factor that makes equations that don't work and makes them work. But it does have there's a foundation for it. So let me first introduce this idea of a, where am I at? So, yeah, here we are. Okay, so we have a phenomenological, I'll write this out. Phenomenological model. Okay, and remember, a phenomenological model is just an equation that I just kind of come up with that makes sense, and the equation I'm going to come up with is one of enthalpy. Okay, so I'm going to generate an equation for enthalpy, and I'm going to insert that into delta G, and I'm going to be able to describe Henry's law, Raoult's law, and the spaces in between, and what comes out of it is this thing called activity. And activity explains all of this, right? So, again, the saving grace of this is that I don't like activity, I don't like Henry's law, Raoult's law is okay, I don't like the word Raoult, that's weird, too French. But the reason, I would probably just totally drop this if it wasn't on your MCAT. But what I do like about this is that I can have a phenomenological model that does explain it. So it's not just totally made up. Okay, now another thing I like about this is that it's kind of clever how it's engineered. For one, I've got, notice I'm leaving a space, nRT. Okay, what I like about this is that it's temperature dependent, it has the right units, and it scales with mass, right? Now this is energy, it better be extensive because RT is not extensive. This makes it extensive, this gives it the right units, and it's temperature dependent. Now the problem is that I've got to be able to make it equal to 0 if I don't actually have a solution. So again, if I haven't diluted B yet, then there is no excess enthalpy. Remember, this is an excess function. Remember that? Excess H. We talked about that 2 lectures ago. Thermodynamics of mixing, when the variables we've had when we talk about mixing, they're called excess functions. Okay. Anyway, all right, makes sense. Again, has got to be 0 when you're pure A or pure B. And I just really like this. You just multiply by the mole fractions of both. See, isn't that clever? Because if you have a pure solution, one of them is 0. And it maximizes at 50-50. If you plot x times 1 minus x, you actually had to do it on the homework, I believe, you'd find that the maximum is at 50-50, which again makes sense. There's one last bit, which is that you know that salt and water tends to get cold, and other things tend to get hot. Some things get really hot, some things get really cold, some things don't really do anything. All right, to take care of that, okay, this is BSE. You come up with a number that gives it magnitude and size. So all of this makes sense. Right units, size extensive, temperature dependent, makes it 0 if you don't have a solution to begin with. I mean, yeah, you gotta have that. And something that says whether it gets hot or cold and how much. Right, phenomenological, but I swear to God, this totally makes sense to me. It won't be perfect. In which case, therefore, delta G mix. How am I doing on time? Yeah, let me just write this out, and then we'll go into more depth next time. Because actually, normally, I've only got like 10 more minutes left. It's just that I think I've thrown a lot at you, so I'm just going to stop with this. Just hold on 1 second. Okay, so I'm not doing the per molar form right now. I've got chi A, ln, chi A. So right now, this is what I've done before. This is the fix to, right now I'm doing the Raoult's law part. If I stop here, I've done Raoult's law. This is ideal. There would be no excess enthalpy because this is what I've derived before. Now I insert the excess enthalpy, and so I've got energy on the outside, so I just end up with beta chi A chi B. Okay. All right, there's that. And what I want to do is introduce the idea of activity. So next time, here we go. Activity. Let me define it. This is kind of nutty. Let me find this. So remember that we're looking for a replacement for this thing right here. So remember that if I had this guy into these chi-A's, I wouldn't need this. It would be perfect. And what I do is I set this equal to gamma A chi A. And let me see, what is the activity? And the activity, and this is the activity of A. Okay, so real quick, and then we'll take a break, and then I'm going to do a couple problems. We'll break early. So notice that what I've done here is that in Raoult's law, this correction factor is the pure partial pressure. In Henry's law, this correction factor is just Henry's law coefficient, just something else. In an activity sense, it's anything, it's any number that gives you the solid line. Right here, K gives you the right number, but not when you're here. Here, the pure partial pressure gives you the right behavior, but in between, you just come up with a gamma that makes it work, and you call it activity. Okay, so what I'm going to do next time is show you that activity is hiding in this equation. And of course, it's hiding right here because that's where I've added it. So activity is actually hiding in this equation. Next time I'll go over that so we can have a 10-minute break.